Welcome everybody to the afternoon session of today, the last session of this workshop. And the first talk is by Joshua Ibai. Sorry if I pronounce your name incorrectly. And he will talk about axion stars toward the Planck scale. Please, Josh.
Great. Thank you very much for the introduction, and thanks to the organizers for this really nice workshop. I've enjoyed it a lot, and I appreciate the invitation to talk. So today I'd like to tell you a bit about axion stars, which we've heard a little bit about this morning and in pieces throughout the last couple of days. What I'd like to tell you specifically concerns axion stars as the decay constant of axions approaches the Planck scale. And my talk has basically two parts, and there are basically two takeaway messages here on the title slide. Takeaway message from the first half is that it's dangerous to extrapolate the properties of axion stars to large decay constants, where large means larger than about 10 to the 17 GeV. I'll explain this in detail. And the second part of my talk is related to detection of axions, looking for cases where we can discover axions at large values of f, and we think we have identified a way to do this, so potentially. So let's get started. So of course, we're now very familiar with the general axion model parameter space here in the space of particle mass m and inverse decay constant 1/f, and I've sort of cherry-picked a few models that make the point I'd like to make, which is partly that models of axions with large f are not fine-tuned. They're not particularly strange or unusual. They are sort of all over the place, and they can span a wide range of axion masses. So here are just a few examples that I found in the recent literature. The things that we want to take away from this sort of zoomed out picture are firstly that couplings of the axion to the standard model are generically suppressed by 1/f. This is part of why searching for axions at large decay constants can be so difficult. Secondly, these two mass scales, the mass and decay constant of the axion, generally determine the axion self-interaction potential. So it can take this, what I've called a sort of generic form. Basically, this is a very common axion or ALP potential that respects the shift symmetry if the axion is a pseudo Goldstone boson. A little bit later, we'll focus on the QCD axion potential, which is similar, but has this weak dependence on the ratio of quark masses. By way of motivation, let me explain why we became interested in axion stars at large f. First of all, there is a vast literature on a wide variety of axion models, and we should leave no axion behind. We should try to test these models at all scales. But in the particular case of axion stars, there are a couple of observations that caught our eye. For example, there have been papers suggesting that axion stars, which have scale decay constants and masses of order 10 to the minus 10 eV, can have roughly the size and mass of neutron stars. They can be very heavy, nearly a solar mass, and very compact. And so if they collide with neutron stars, this would give rise to really interesting gravitational wave signals. And through axion conversion to photons, so sort of a multi-messenger picture with rapid conversion of axions to photons. So you could see this in multiple channels. So we thought this was very interesting. Secondly, there have been a number of papers, including from people in this virtual room, suggesting that when axion stars collapse, if they have nearly Planck scale decay constants, then they can collapse directly to black holes, which is an unusual thing for axion stars. As I'll explain later, the typical process for axion star collapse is to collapse and sort of explode in a burst of relativistic axions. Generically, axion stars do not form black holes. So it's interesting that Planck scale ones maybe can. If they do, this could explain, for example, intermediate mass black holes that are hard to explain with standard black hole formation mechanisms. These are just a few motivations for us. And I'll also mark out a particular spot on the QCD Axion line just to take some parameters later so we can make some numerical estimates. So 10 to the minus 5 EV and about 10 to the 12 GeV. Okay, let me start by telling you what is an Axion star. We have heard a bit about this in the last few talks, especially in the morning. But generally for me, an Axion star is a configuration of axions that lives in this phase diagram. And this phase diagram can be separated into basically 3 parts. There is the upper part, the most dilute part, where the mass radius relation is actually inverted. R goes like 1/m. In this regime, the bound configurations of axions are very non-relativistic. Newtonian gravity is very sufficient for the calculation here. The leading self-interaction appears at the sort of endpoint of this branch, but generally speaking, self-interactions are unimportant for these configurations. And importantly, these are stable as long as you stay below a particular maximum mass. This maximum mass corresponds to the turn on of the leading self-interaction, which is generally attractive. So when this self-interaction turns on, it actually destabilizes the star, and that's what leads to collapse. But as long as you stay below that maximum mass, you can simply solve the Gross-Pitievsky-Poisson equations. It's basically a nonlinear Schrodinger equation coupled to gravity. And the solutions are easy to find. So this is generally what's now called a dilute axion star to distinguish from the others. And these solutions were found in the first place, many decades ago. A second sort of intermediate regime for axion stars is what is sometimes called a transition axion star. These are not really stars because they're not really stable. These are actually metastable configurations. If you think of sort of extrema of the action, these are sort of maxima of the action. So they're unstable under perturbations, but they're still non-relativistic. In these configurations, the self-interactions start to become important, but only the leading one. They're actually balanced by an attractive self-interaction and a repulsive gradient energy. And at the largest masses on the transition branch, you start to see a turn on of some decay processes, which I'll discuss a little bit later. And thirdly, we have this most dense branch of axion stars. These are characterized by very high densities, where the field value is roughly of order F. This means that all orders in the self-interaction potential actually become important. And you should not be using the Gross-Pitievsky equation because this is the non-relativistic approximation. You need to return to the full Klein-Gordon equation. And what people have done, some people do simulations of the full Einstein-Klein-Gordon. But as I'll explain, you can use a perturbative approach basically to integrate out the high energy modes in terms of the back reaction on the low energy axion physics. And you can do this perturbatively. So I'll explain in a little bit. So we've heard about these configurations also under the name of exciton, but these days many people prefer to call them dense axion stars, even though again they're not really stars because they're not really stable. They decay very fast due to these relativistic processes. How we actually handle these relativistic corrections to the non-relativistic theory has actually spawned a lot of literature. Especially over the last 5 or 6 years, there have been at least three to five independent groups developing different frameworks for characterizing the deviations from the non-relativistic limit, both for axion stars and also for sort of generic scalar fields. So it could also be important in cosmological settings. And you can see that some of the early work neglected the effect of gravity, but this actually doesn't allow you to characterize things like dilute axion stars. Different theories have taken into account different aspects of decay processes, which are sometimes called classical, which are sort of tree level decays, and quantum, which are, they're sort of loop level. So in any case, I will just flash this slide for you for your perusal later. But let me just point out that the work that I'm telling you about today is based on this paper from late 2020. And it's already not the cutting edge because there is a new paper out a couple of months ago that actually takes into account next to leading order corrections in GR. So that's kind of fun. Okay, let me just give you one slide about our method because it's fairly technical, but we can just get to the punchline pretty quickly. So the basic insight behind our method is to be found in one of the earliest papers on boson stars from Ruffini and Bonazola. The way that they characterized boson stars was by starting with the full Einstein-Klein-Gordon equations and then expanding the scalar field phi linearly in creation and annihilation operators, and then dropping any term that was not the ground state. So then you end up with a sort of single field in your expansion, the Axion wave function R, and the energy is given by this exponential factor where mu naught is the eigenenergy or the chemical potential, if you like. And they found some of the first configurations we now call boson stars. In our method, we basically generalize this operator to take into account the various relativistic contributions. In the first place, of course, if you take our field operator and you restrict to only k equals 1, you recover the original Ruffini-Bonazola result. And we showed that in the non-relativistic limit, this recovers exactly the Gross-Pitievsky-Poisson equations. We showed exactly how you take the limit. But this allows you to go beyond. So by taking into account k greater than 1, you can actually calculate the back reaction of higher energy modes of energy k mu naught. These are like higher harmonic or ringing modes inside the Axion star energy. And you can not only calculate this back reaction, but it can be easily organized as a power series in a small parameter, which we call delta. So delta tells you how far the eigenenergy is from the mass. So when the eigenenergy is very close to the mass, you're safely in the non-relativistic limit. And when mu naught is very far from m, delta approaches 1, and you deviate from non-relativistic physics. And thirdly, we have a contribution here from scattering states in the theory. These are states with energy greater than the mass. And it's very straightforward in this calculation to determine decay processes by just taking transition matrix elements from n cold axions in the star to n minus n cold axions plus some relativistic ones that are emitted. So this is how we take into account decays. And let me give you one view of the results. So this is a direct comparison of our leading order relativistic calculation to the fully non-relativistic Gross-Pitievsky-Poisson equations that some have used to characterize the dense branch. And you see a couple of things here. So firstly, there's a large deviation between the two, just telling you, as expected, relativistic corrections are important. But secondly, if you just continue calculating the Gross-Pitievsky equation, there's nothing in that equation that tells you need to cut off your solutions anywhere. So you just keep on calculating up to arbitrarily large mass, and it leads you astray. In the perturbative calculation, of course, you know how well you can control your expansion just by taking the expansion parameter up to some particular value. The other thing to point out is that within the same calculation, we can calculate the stability of the Axion star to decay, and we find that states all across the dense branch and on part of the transition branch are unstable to decay. And the transition from stability to instability is very rapid, I should point out. So states on the solid line have lifetimes much, much smaller than the age of the universe. In fact, decay processes are basically negligible when the star is stable, and it very rapidly transitions to exponentially fast decay, and essentially the star disappears. So we basically, in the recent work, we just used this whole formulation, and we wanted to extend it to the case where the decay constant approaches the Planck scale. The only additional wrinkle here is that normally calculations on the dense branch and the transition branch can neglect gravity because there's usually a wide separation between the dilute states and the dense states. But as f approaches m Planck, the two branches come closer and closer together. And in the intermediate regime, you need not only relativistic corrections, but also at least leading order gravitational, the Newtonian potential. So we took these things into account, and this is what we found. This is the result. So this is, again, on the left side, the radius versus the mass for different choices of the decay constant, going up to about 10 to the 18 GeV. this is where you start to worry actually that post-Newtonian corrections to the gravitational potential will be important. So we had to cut off our calculation here. And you see a couple of things. So firstly, as you increase the decay constant, the transition branch shrinks as expected. So this is what I told you before, but also the extent of the dense branch on which you can make a calculation consistent with the perturbation theory also cuts off. So you see this sort of shrinking of both transition and dense branches. But even more importantly, for phenomenological purposes, the states that are unstable to decay, which are given by the dashed line, actually start to creep onto the dilute branch, which is considered very unusual because this is usually the stable branch. This happens around 10 to the 17 GeV. So about 10 to the 17 GeV, the dilute axion star at the critical mass is already unstable to decay. And as you increase the decay constant, it creeps further and further onto the dilute branch. This is what I mean when I say it's dangerous to just extrapolate these results, because some of the dilute states are actually not stable. And you can see the same thing in the right curve. Basically, this is just showing the mass as a function of basically F. And you can see that above about 10 to the 17 GeV, the decay instability is the stronger limit compared to the gravitational instability. Okay, so that's basically the first part of my talk. In the second part, I would like to tell you a little bit about detecting axions. As I pointed out, of course, detecting large F axions is a big challenge. I don't think I need to convince anyone of that. So this is a recent work of Andreas and collaborators showing this trap misalignment axion and some proposals for the future of axion physics to detect the axion photon coupling. And you can see that, even in the sort of farthest reach one can reach, maybe one can reach the Guts scale, but to truly get to Planck scale axions is extremely difficult. So one motivation for this is maybe that it would be nice to look for systems where the largeness of the decay constant is not such a bug that it actually could be a feature. And I like as an example, axion black hole superradiance. So I don't really have time to go into this in detail. I'm sure many people know the story here, but basically rapidly rotating black holes can generate axions. There's an instability in the scalar field that converts the angular momentum of the rapidly rotating black hole into axions that are in a high angular momentum state. And this spins down the black hole. So if you observe the black hole, that means the axions aren't in the theory, and so you can constrain axions. However, if the axion self-interaction potential is large enough, then this superradiant cloud becomes unstable and it collapses and it fails to spin down the black hole, and your constraint sort of gives up the ghost. So when you see these superradiant limits, generally they are coming from the bottom of the 1 over F parameter space, right? Large values of the decay constant actually give you a better constraint, and small ones give you a worse constraint. So we wonder if there are systems like this. And here is a system like that. I told you before what happens when axion stars collapse. Some of the details of how this works were worked out in a very exciting, about 3 weeks of time in late August and September of 2016. 3 papers came out in the same span of 3 weeks. I'll be focusing on the second of these papers, which is a simulation by Levkov, Panin, and Ketchev, which really nailed down this process, extremely well in great detail by actually simulating it. But here's the basic story. So suppose you started with a stable axion star that lives on the dilute branch, and you allow it to grow in mass. We've heard a bit about accretion and mergers. It's very unclear exactly how this goes. It depends on a lot of details of axion physics and cosmology. But suppose stable axion stars can eventually reach their critical mass, and at that point they would collapse gravitationally. This collapse for a long period of time is non-relativistic and spherically symmetric. So it just sort of collapses in on itself at fixed mass. And then at some point, these relativistic processes turn on. And so you get rapid conversion of axions to relativistic axions, which are emitted from the star. So if you'll excuse my explosive slide transition, this is what is sometimes called a Bosenovae. And in this explosion, a large fraction of the mass of the Axion star can be emitted in relativistic particles. And because the mass of the Axion star, the critical mass is actually proportional to F, this means that the bigger the F, the larger the explosion. So this is actually potentially a handle on larger F axions. What happens after the explosion is still, I think, a little bit open for debate. In the simulations, they show that the non-relativistic component that remains behind remains gravitationally stable, but in a not settled Axion star sort of configuration, a sort of diffuse gas that is gravitationally bound. So maybe over time, this thing can eventually reform or relax, but I think that that's more speculative. So we'll just leave it at that as a comment. So let me tell you just a couple of details of this simulation. I run the risk of explaining the simulation to the simulators, which is not what I intend to do, but I need to tell you a couple of details that we took from their work in order to make the sensitivity estimates that we made. So first of all, when the Axion star collapses, it hits some sort of hardcore repulsion and it explodes. But when it explodes a number of times. So each explosion is relatively short, but it can happen, n of order few times before finally the relativistic axions escape and the non-relativistic axions are left. In any one of these explosions, the duration is fairly short. So it's only a few hundred 1/m cycles in the exploding star. So this is one thing we took from the simulation. Note that there are multiple explosions, as I said. In our analysis, we took just one of them. Although if you look at 5 explosions that are happening rapidly in succession, we think that should only strengthen our signal. Secondly, and very helpfully, in the simulation, Levkov, Panin, and Kachev showed the differential energy spectrum of the emitted axions. So you see this large peak at low K, which corresponds to non-relativistic axions, and you see this multiple peak structure going down at large K. So there's a peak at K/m between 2 and 3, between 3 and 4, between 5 and 6. They're roughly equally spaced as they go down. What we did in our analysis was basically just take the first relativistic peak, which corresponds to K of order 2.5, and with a momentum spread of order M. And we integrated the energy in this first peak just using basically what's given in the figure. So if you just take the energy in this first relativistic peak, you get a total energy of 10 to the 41 GeV, which is, I don't remember exactly, it's a small fraction of a solar mass, but it's also a strong function of the decay constant. So this thing actually can also grow fast. I'll point out just very quickly that in the simulation, they were using the QCD axion potential as opposed to the sort of 1 minus cosine form. And it's unclear exactly how the results would change with different potentials, but we've used their results in sort of a general ALP parameter space, but for the QCD axion potential, which is what they used. I'll also just point out that there are these higher order relativistic peaks, but we ignored those also in our analysis. So this is the thing we'd like to detect. And if you, to make a sort of first pass at the sensitivity, compare what we get for a relativistic axion explosion to what you look for in a dark matter search. So in a dark matter search, there is a fixed local density, 0.4 GeV per centimeter cubed. But the reason axion experiments are generally so sensitive is because you can integrate over many 1/m cycles coherently. You can coherently gain signal for many axion oscillations. One way to put this is that the quality factor in the axion oscillator is very high. So it's like a 10 to the 6 quality oscillator. On the other hand, those two things are both different for us. So the energy density is in principle whatever it is. It depends on the total energy in the burst, the distance of the burst from the detector, this R, and also the duration of the burst. The energy is not all emitted at once. It's emitted over some time scale, which I will call delta X burst. And if you just plug in the numbers that I gave on the previous slide, you find that the energy density in the burst at the position of the detector can be 6 or 7 orders of magnitude larger than the dark matter, but only for relatively nearby explosions, just barely out of our solar system. So that doesn't sound so great. The other downside is that these are relativistic axions. They have a wide momentum dispersion as opposed to a narrow one. So this is a poor quality oscillator. So you can't integrate coherently, it seems. So it seems like you maybe lose in both places. Naively, you might guess that our sensitivity relative to dark matter will scale like this. So this is the square root of the ratio of energy densities times the ratio of Q factors, which is, by the way, the scaling found by Hitoshi Murayama and his group looking for relativistic axions from cosmological sources, sort of a cosmic axion background. And if you again plug the numbers here, you find that this ratio is only smaller than 1 when explosions are relatively nearby. So this doesn't look so good, but hear me out. Before I tell you why we still think it's interesting, let me tell you why it's even worse than I said. So what I told you was that the axion burst will be spread out over some intrinsic burst duration. That's actually worse than that because the momentum spread will actually grow as the wave travels in flight. If the axion burst is not right next to us, then just normal wave spreading will dilute the signal. So even if you start from a very sharp, high density pulse at the source, by the time it gets to the detector, it will be very wide and low energy density, which sounds very hard to detect. So actually, contrary to what you might have thought, the energy density won't drop as R squared. It may drop even faster as R cubed, the energy density at the detector. So that doesn't look so good. However, this can be compensated by 2 facts. Firstly, even though the energy density decreases, the burst duration is growing at the same time, and in fact, by nearly the same factor. So as long as the burst duration isn't so long, if your experiment runs longer than the burst, you can still capture all of that energy density just integrated over time. So actually the total duration of the burst is also proportional to R, as opposed to merely some factor over M, as it would be if you just use the intrinsic burst duration. Secondly, and maybe more strikingly, even though the waves emitted from the source are sort of incoherent low quality waves, due to this wave spreading effect, the momentum modes within the pulse will actually separate themselves in flight. So the fastest axions reach you first, and the slowest axions reach you last. And at any given time in the detector, the effective momentum spread is very small. This means that the effective coherence time inside the detector can actually be relatively long, contrary to what you might have seen if you just observed this right at the source. So because of these 2 effects, actually, you can gain back most of the signal that you would have lost based on this, sort of naive wave spreading story. I think I'm probably running out of time, so let me get to the results. This is basically how we propose the search strategy. So we worked out the sensitivity ratio in detail beyond this naive guess, taking into account all of the relevant timescales. So in the numerator, this is the usual dark matter coherent integration of the dark matter signal. And in the denominator, we have the burst duration and the coherence time in the burst. And what this ratio tells you is, if you had a dark matter experiment sensitive at some frequency, would it be at least as sensitive to the relativistic axion signal at the same frequency? So you can look at the ratio, and of course we did, but in order to take absolute sensitivities, we used the long-term reach sensitivity for abracadabra, which is given in this 2016 paper. Abracadabra is a good example for us because they can run in a broadband mode. This is the mode you would want to run in to detect transient signals like this. You don't want to be trapped in the wrong energy bin, the wrong frequency bin, if a burst is going to occur rarely and only in some other bin, right? You have to be sort of additionally lucky to be searching in the right place. Though see, of course, DM radio and shaft for very related experimental searches. The other sort of consistency check here is that you would like for there to be enough bursts around that you would see one realistically in a year of experimental running. So in order to make this estimation, we had to plug in by hand a sort of lifetime for these bursts. And this depends on very complicated physics of accretion, of what is the mass distribution of Axion stars, all of this kind of stuff. So it's very worthy of a detailed study, which we hope to perform. But in order to just see what the sensitivity might be like, we took a sort of astrophysical timescale, like the lifetime of the galaxy, in order to estimate the lifetime here. And just asked whether there is, on average, one exploding Axion star within a radius r within a year of an experimental running. And here are some results. So this is for the photon coupling. This is the sensitivity ratio I told you about, and this is for Abracadabra specifically. So let me walk you through it. Firstly, looks like it didn't come up. Oh, sorry.
Josh, you have been speaking by now half an hour.
Can you see the bullet point? No. Okay. Here they are. So we'll start at 1. So this is again 1 over F versus M. These are the sensitivity bands for Abracadabra at different explosion distances, 10 to the 3 AU, parsec, and 10 parsec. So you see that for explosions as far away as 10 parsecs, Abracadabra would be sensitive. And notice that the contours are vertical. This is again because while the sensitivity goes like 1 over F, the signal is also proportional to F. So in the product, these are independent of F, and so you're sensitive at any value of F essentially. If you're sensitive at one value, you're sensitive at any F. So that's interesting. Secondly, this gray contour I'll just point out to connect with the first part of the talk. Axion stars for F larger than 10 to the 17 GeV won't undergo this usual collapse and explosion thing because the states on the dilute branch are unstable. So we basically cut those out of the analysis. Thirdly, look at the red lines. So the red lines are this other sort of sanity check. How many of these bursts can you reasonably expect to happen within an experimental timescale? And so if you look, for example, at the parsec contour compared to the parsec red line, you see that the overlap happens, at relatively low F. That means that the sort of explosions you would want to see are infrequent, given the assumptions that we put in. So this is unfortunate. We think you can possibly model build around this. For example, if there's some astrophysical or cosmological reason that Axion stars are only exploding now, then the lifetime that we put in by hand can be smaller and the red contours will shift down. But this is sort of more speculative. Fourth, notice that in the top triangle here, there's this yellow hatched region. This actually points to yet another very nice simulation of Levkov, Panin, and Ketchev, pointing out that as Axion stars collapse, in a particular range of Axion photon coupling, they can convert to photons through parametric resonance, rather than, in addition to, I'm actually not sure, relativistic Axions. So I would love it if this could be clarified for us. But essentially, we just treat this as yet another interesting fact about Axion star collapse that maybe is worth investigating further. Briefly, let me tell you about the nucleon couplings. So in principle, for nucleon couplings, we should do much better. This is because Axion couplings to nucleons are generally proportional to the spatial derivative of the Axion field, which means they're proportional to the velocity of the Axion field. And in a dark matter search, this is basically 10 to the minus 3. So your sensitivity takes a 10 to the minus 3 hit. Whereas for us, these are relativistic particles. So V is order 1. So in principle, we should do 10 to the 3 better than dark matter searches, over and above what I've shown you before. So in this figure, I basically show you just the sensitivity ratio, where this ratio is less than 1, meaning more sensitive to relativistic bursts. And you see that over a wide range of parameters, the sensitivity to relativistic axions is actually much better than dark matter. On the other hand, there are not strong broadband searches for nucleon couplings, much to our disappointment searching the literature. So if you ask the question, how strong of a coupling do you need in order to detect axion bursts at a given distance? The answer is that you have to be fairly fairly sensitive. So in this figure, I show for comparison the Casper wind projection, as well as projections from comagnetometer searches, but these are both resonance searches. What we would need is a very sensitive broadband search for Axion nucleon couplings. And as far as we know, it's just not out there. So, we would love to see that. In 0 minutes, I would just want to tell you about a sort of generalization of this. So of course, we applied this to the specific case of the Axion Bosenovae, but all of the machinery in terms of calculating this sensitivity ratio and all the coherence times and so on, this can be applied to more general relativistic Axion bursts. So you could imagine these things happening in mergers, or again, because of super radiant clouds around black holes and mergers. There are lots of astrophysical processes that could possibly produce large bursts of relativistic axions. And you might want to know what might an experiment like Abracadabra, for example, be able to search for just in terms of a generic axion relativistic burst. So in order to do this analysis, we basically take the total energy of the explosion as a free parameter, contrary to the Bosenovae case where it was fixed by the simulation. And we also had to assume something about the burst duration and the spread in momentum. So we took optimistic choices for both of those just to see what the reach might be. And this is what you find for Abracadabra. So in the left curve, we fixed the number of explosions per experimental time scale to 1 at a given radius. And what you see is that at different radii, the same experiment would be sensitive to explosions of very different scales. So for explosions of 10 to the 18 M solar, you would expect 1 per experimental time scale at a distance of 10 to the 3 AU that is detectable. And for kiloparsec, it's 10 to the -4 M solar, and so on. So that's pretty neat, we think. And if you sort of average over this sort of free energy parameter and just ask, for any kind of explosion, what is the farthest reach you could find at fixed n, you arrive at the curve on the right. So for n of n equals 1, you end up with this curve. And if you want many more explosions per experiment, you get the upper curve. And if you allow for relatively infrequent or low lifetime explosions, then you get the lower curve. Okay, so in conclusion, I would like to reiterate my 2 sort of take-home messages. Firstly, in the first half of the talk, I will just caution anyone who's interested in Axion stars at large decay constants to not merely extrapolate the results at low F. And secondly, we think these relativistic Axion bursts are really interesting, both in the specific Bosenovae case where the details have been worked out by simulation, and also in the general case where this might be happening from general astrophysical transient sources. I'll just point out quickly that this is maybe complementary to dark matter searches in the sense that this can possibly probe the Axion potential, whereas the usual dark matter searches are totally insensitive to even the phi to the 4 coupling. These axions are produced through self-interactions, so you actually can potentially say something about the strength of self-interactions. And there are some, slightly more speculative implications that we'd like to work out in the future. Okay, thank you very much for your time.
Okay, thank you, Josh, for a very enthusiastic talk. You basically ate up most of your time for questions, but we can have, we can take a couple, perhaps. So are there any questions? I have a quick question while people are thinking what they want to ask. In the beginning of your talk, you were talking about this dense branch where you developed the perturbation theory to calculate that. And at some point, this perturbation theory breaks down, so you cannot calculate any further. So is there any understanding that there is nothing or any arguments that there is nothing interesting happened beyond that point? I mean, is it worth investing time in that, or it's obvious that there is nothing?
I think there are honestly differences of opinion in the literature on this. So maybe that means it is interesting. My point of view about it is that it just from the point of view of the equations of motion, it's not clear where anything new can possibly appear, right? So unless you could go up to large enough axion star masses that you start to turn on general relativity, in which case, many things can change. But I don't know. My personal point of view, which not everyone would agree with, is that probably you don't need to calculate very far on this dense branch to basically get the picture of what's going on.
Thanks. Any other questions? I don't see any.
Oh, I think maybe Dima is talking, but he is.
It's Dima. Sorry, I cannot raise my hand because I'm a host. Peter, can I ask a question?
Sure.
Okay, so actually a short comment and then a question. Actually, a comment about the burst into the photons and burst into the axions. Actually, there are two lines. Number one is number one is like roughly 30 times larger than the KSVZ coupling. Is if coupling to photons is above this line, then the collapse starts, the star shrinks, and then a resonance into photons begins, so it starts to burn axions. So what you get back is partly axions, partially photons. And if axion coupling to photons is larger, then this starts faster. So star shrinks a little bit, and then resonance starts. But if coupling is 100 times larger than the KSVZ, so 3 times, this is a short strip, okay? So between 30 times times the KSVZ and 100 times larger than KSVZ. So if the coupling to photons is large, suddenly these collapses do not happen at all. That's what we observed in our paper, because the stars, they grow to some mass smaller than critical, then the resonance just begins, it burns part of axions and stops. So this is a very stable process. You add axions to the star, but the resonance into photons burns them. So probably it's worth putting two lines here, and at very large coupling, the Bose stars, they are like glow like the usual stars, but in radio. Yeah. So
Dima, now you are spending your time, huh?
Sorry, I have a short question.
The time of your talk.
Okay, a short question is probably, did you consider a possibility where there is a collapse, a stream of axions, and then there is a magnetic field between us and the source, and these axions convert into photons in magnetic fields?
That's very interesting. So first of all, thank you for your initial comment. That's very clarifying. So we will, I'll discuss it with everyone next time we meet, and we'll look closely at your paper for this second line. And in terms of the magnetic fields, no, we did not look at that, but I agree that that's very interesting. So then you could directly observe the sort of radio frequency axions coming in, as opposed to the very difficult task of detecting the axions. Yeah, very interesting. Thank you.
Okay, I'm afraid we have to cut now, even though nobody is, well, anyway. So thank you, Josh, again.